Start off slowly then, while the audience walks in, okay? Hello everyone, and welcome to Cisco Live. Today's topic, it's about ASR1000 OTV Encryption and Redundancy Deployment. In the next 2 hours, we'll be mostly talking about all the architectural aspects of OTV and how we can implement redundancy on top of it. We'll touch upon a bit on a special design topology that we worked on with the customer and give a redundant setup, put a redundant setup onto the OTV feature. A little bit of introduction about myself. I am Umar Mohanty, working with technical services in Cisco from past 4.5 years' time. Okay, at any point in time, guys, if you have any questions, feel free to interrupt me. I'll try and answer it then and there itself. Just keeping the time considerations in mind and just to keep the room available for the next speaker to walk in. I might park some of those questions towards the end of the session during the Q&A. Alternatively, what you can do is you can use the Spark room to post your queries. It will be available till 3rd of July. So we have a lot of time actually to discuss a lot of things about OTV encryption. Moving ahead, before we go ahead, can someone help me decode this message? I'll give you a moment. Anyone wants to give it a try? And whoever decodes this, I'll surely treat him today, after the session. Okay. He gave you a hint. One of them is A, correct? Okay, let me decode that for you. There's never been a better time to present at Cisco Live. A very simple form of encryption, guys, I used over here. Each and every alphabet in the English letter, I just assigned it to the corresponding number. So why do we need encryption in the first place? And that too on top of OTV. OTV, or Overlay Transport Virtualization, is a technology that fits into data center interconnect. It really doesn't care about the underlying transport layer. Be it IP, be it MPLS, it'll still be able to provide you services on top of it. So when we are exchanging some of our data center traffic over the MPLS cloud, there are chances that anyone can sniff that data and get all our critical information. Even some of our data protection laws and some of the compliances in our company suggest that any traffic that goes out of our edge devices needs to be encrypted, right? I was just going through one of the sessions yesterday, the Network Intuitive, which we have just come up with like a week back. The session was from our SVP, David Grockler. An interesting slide in that I found out. According to a survey, currently it is near about 55%, more than 55% of our data flows as encrypted. And it is expected, in the upcoming 2 years, by 2019, we'll have more than 80% of the data going as encrypted over the cloud. That's how important it is at the moment to think of DCI encryption. Whatever traffic leaves in a secure manner to our data center. With this in mind, let's move on to the agenda, short one. We start off with the dub of OTV, or what and why of OTV. We'll discuss about all the architectural aspects of OTV itself. Then top it up with the role of ASR1K in OTV deployments. Then comes the most important part of this presentation, that is OTV with encryption. We'll talk about the modes of encryption that we can use on top of OTV. I'll touch upon a bit on a design topology with OTV with redundancy, how we can make our OTV setup redundant. I'll then summarize the session with a few key takeaways from this presentation, and I'll open the room for any questions. Hope that works for you. Please don't bury me with the questions. Okay. OTV, Overlay Transport Virtualization, it will help us achieve these 3 main things. Any workload in that matter would mean applications, be it any kind of high availability protocols, be it any kind of clustering technologies, OTV will be able to provide us services on it. Anytime and anywhere in that matter, as I said before, it is completely agnostic to the underlying transport layer. IP, MPLS, be it anything, OTV will be able to provide us services on top of it. The session will mostly focus on the architectural aspects of OTV and some of the deployment scenarios with encryption, the modes of encryption that we can use on top of OTV. We'll touch upon a bit at the end on a special design topology that you can implement to make your OTV setup redundant. By the end of this session, I hope everyone in this room gets a better understanding of the control plane and data plane of OTV and how they work together towards extending your VLANs and adding encryption on top of it. What this session doesn't include would be some of the path optimization technologies and some of the workload mobility solutions and design considerations related to it. I hope everyone is in the correct room. You expected this, right? Okay. Let's talk about the distributed data center goals. Some of it are pretty obvious. My business should always run. Be it in any geographical location, I should be able to traverse data across it. Some of my users, they might be somewhere in Australia, and the application server they're trying to access, it could be somewhere in the US. Yes, due to the geographical distance, there might be a bit of latency, but still, OTV will be able to provide you services on top of it. That gives me a segue to talk about the distributed applications. I might have deployed all the applications all through the globe, all around my data centers. It's just not deploying those applications won't help much. We need to interact with them. We need to talk to them. Being at any particular location, I should be able to interact with those applications. Seamless workload mobility. Think about a VM. Let's say the VM was somewhere in data center A, and there is a need that I move that VM to one more data center. Without any kind of manual intervention, I should be able to provide the same services it was having in data center A, in the previous data center. The last point I want to stress on, maximize the compute resources. Think of a disaster recovery site. What does it do? Just sits idle till your active site goes down at one point in time, and it takes over all the application and user traffic. But why keep it idle? We can push some of the applications to that site, keep the CPU busy, give it a load. What we achieve via this, a bit of load balancing on the traffic. All of these goals we would be able to achieve it by using OTV. Let's have a look at some of the current data center solutions. EO-MPLS, it's a bump in the wire, but would require MPLS to work on. VPLS in that matter, think of it as a switch in between your data centers that will provide you all the MPLS solutions, but would require a full mesh connectivity of pseudo wires. It's a very tedious job for a network administrator, very hard for the network administrator to go ahead and troubleshoot on some of the pseudo wire related issues. Pretty hard to maintain. I have a picture in the upcoming slides. If you think of these pseudo wires in a physical manner, that is how it will look like, and believe me, it's a mess. It's very hard for the network administrator to go ahead and troubleshoot on them. Just troubleshoot on a few pseudo wires at any point of time which has gone down. So these are some of the challenges with our layer 2 VPNs, and OTV will be trying to achieve these three main pillars. The flooding behavior. We want to stop any kind of unicast, unknown unicast being propagated towards the other data center. We want to stop that at the edge device itself. Pseudo-wire maintenance. This is the picture I was talking about. Look at it. It's all jumbled up. We want to get away from this pseudo-wire maintenance itself via OTV. There are features in OTV which will help us get away from the pseudo-wire maintenance, negotiate on the control plane itself. We need a full mesh connectivity in VPLS, as I told you. And for n number of sites, we would need near about n cross n minus 1 by 2 number of pseudo wires. That's a big number if you consider 4 or 5 data centers together. Last but not the least, it's the multi-homing feature. Let's talk about some of the historical or some of the multi-homing solutions that we have with the Cavalry 6500s. VSS, stacking, multi-chassis ether channel. What do we do in them? Bring up two boxes, join it via a few links, bundle it together, put some intense config onto it, and the whole box will be working as one. At the end of the day, there are two different boxes. We want to integrate it, we want to make it more dynamic via OTV. Let's talk about the features which will help us achieving these three pillars or overcome these challenges. Dynamic encapsulation. This is a feature in OTV which will help us achieve those challenges which we spoke about. We get away from the pseudo-wire maintenance, and what we do is now negotiate on the control plane itself over the dynamic encapsulation, via dynamic encapsulation as well. Optimal multicast replication. If we think of a hidden device producing multiple copies of our traffic and sending it towards the neighbor, in today's WAN network where bandwidth is a crunch, it's a bit inefficient. With dynamic encapsulation in OTV, what we do is we let the core do the replication for us, not in the hidden device. We save some bandwidth there. Multi-point connectivity and point-to-cloud model in that matter would mean, like, let's say, I want to talk to you. I can do that in two ways, right? First one, broadcast. I can broadcast the traffic. Whatever the message I want to send, I can just broadcast it. Yes, you will get the message, but some of the uninterested parties, somebody passing from that room, via this room, can also hear that. It is unwanted for him. With dynamic encapsulation, what we do is we want to send it to a set or a subset of users who are really interested with that traffic, interested to hear that message. Just adding encapsulation doesn't help much. There should be something else, right? What do we do in GRE? We take the IP packet, put a GRE header on top of it, and send it further. But that doesn't help much. OTV has one more feature, protocol learning. Based on protocol learning, it helps us preserve the failure boundary itself. As I told you before, the unicast traffic, the unknown unicast, everything is stopped at the edge device itself. It preserves the failure boundary. Whatever happens within the site is within the site. It won't traverse those data or those unwanted traffic towards the other data centers. Built-in loop prevention mechanism. Via protocol learning, what we do, if we think about, let's say, if we think about spanning tree, STP has no notion about the MAC addresses, right? A single packet can create a loop in the network. With protocol learning, what we do is we just don't restrict ourselves to know where the destination is, but along with it, we now know whom to send this traffic. With a MAC address as the next hop, as the IP address, or the name of that particular site itself resolved, we can achieve that via protocol learning. Multi-homing. This particular feature is inbuilt. We don't have to put any specific configurations in OTV. To achieve multi-homing, it is all inbuilt under the hood. The last one, site independence. If I think of myself as the edge device, I'll give a notion to the LAN devices that, okay, I might be sending some of the traffic, some of your traffic towards the other data center or vice versa. But at all points in time, I will have the authority over the traffic. I would know which traffic to pass across, which traffic to drop. That's how I maintain the site independence. OTV, the support for OTV started somewhere in XC35 for multicast transport, and unicast transport started in XC39 and later releases. Going ahead towards a comparison slide, this is just a comparison I put through for our older versions, the L2 technologies along with OTV. I'm not going through the whole ones, just a few points I've highlighted over there. If we talk about multi-homing, we don't have that particular feature with EOMPLS or L2TP v3. In OTV, again, it's a built-in feature. You don't have to put additional amount of configs into it to make it work in a multi-homing setup. We talk about loop prevention. In the other technologies, the UMPLS or L2TP v3, it is all point-to-point. VPLS, it's a large STP domain. In OTV, again, it is a built-in feature due to the protocol learning. We talk about manageability. All of these three features, they're pretty config intensive, pretty hard for the network administrator to troubleshoot when it goes to add something, when it goes to remove. In OTV, we need minimal configs and a single protocol would be running. When I talk about this protocol learning and a single protocol in OTV, there's a question coming up in your mind. I can guess that. Do I need to implement some protocol to make OTV to work? No, you don't have to. It's all inbuilt in the OTV feature. It's all under the hood. We'll talk about that protocol in the upcoming slides. Some of the terminologies that we need to use in OTV, that we have in OTV. The edge device. Edge device is the device that is facing your outer wall. This is the device on which performs all the OTV functionalities. We support the support for multiple OTV edge devices is also there. It supports, if you talk about the next one, I'm sorry. If we talk about the internal interface is nothing but the L2 interface or the LAN interface. This is the interface which will carry all the VLANs that we want to extend over to OTV. No OTV configurations are required on the internal interface. It's just a plain L2. Moving ahead about some more, joint interface. Joint interface is the interface from the edge device which faces the outer wall, which faces your MPLS or IP cloud. There is no OTV configurations that is required on the joint interface. We talk about overlay interface. This is a logical interface, and all of your overlay configs would be on the overlay interface. The job of the overlay interface would be to encapsulate those L2 frames it gets from the LAN devices into unicast or multicast, the mode of transport, whatever we are using. That's the main role of the overlay interface, and then it hands over the packet to the joint interface for further routing. The control plane. How do we build the control plane in OTV? As I was talking about, the protocol which runs in the backend is ISIs. Why did we choose ISIs, first of all? Sure. I'm sorry?
It's multi-protocol, so it can route MAC addresses.
Exactly, the second point of yours. It can route MAC addresses. It has the ISO standard TLV extension, which can allow MAC transport. That's why we chose ISIs. We didn't want to reinvent the wheel again, just leverage out of ISIs. This control plane learning is done via MAC address advertisements between the neighbors. Before we can send those MAC addresses or advertise those MAC addresses towards the other site or towards our neighbors, we need to form a neighborship. How do we do that? There are two modes by which we can provide, by which we can build a neighborship. Either it is unicast or multicast. Support for unicast, as I told you, it started with XC39 release. And support for multicast, it started with all shipping releases, that is XC35. So the mechanism that they use, the mechanism it uses to, in multicast transport, to form the adjacency, to discover the neighbor. What it does is, the edge devices would join the multicast group as if it were a server or a client. All the traffic, all the data or control plane traffic that gets replicated in the core and sent towards the other neighbors in the same group. What we achieve via it, the end result. Now we have the multicast neighborship forming over the core itself. A single update message, a single hello packet of OTV It is replicated in the core, sent towards all of the neighbors who are part of that group. There are a few considerations that we need to keep in mind. The requirement for the control plane in OTV is PIM ASM, or any source multicast in sparse mode. The requirement for the data plane is PIM SSM, source specific multicast. This is where the S, G information is populated. Based on the S, G information, it will send the traffic towards the source, towards the core, the multicast core. The core will look at the group ID. Okay, this is part of my group, this is part of this particular group, and based on the source, it will replicate the traffic and send it towards the other neighbors who are part of that multicast group. Now, the mechanism that we use in unicast transport, think of it as a phone book. If I have your numbers in my phone book, then only I'll be able to call you, right? The mechanism that it uses for unicast transport is all of the neighbors register to an adjacency server. Once they register with the adjacency server, the job of the adjacency server is to send the full list of neighbor towards all of them. The end result we achieve, neighborship is automated by the adjacency server itself. It has knowledge about how many neighbors do I have in total, and what do I do after the neighborship has been formed is send the whole list of neighbors towards the others, so that they know how many edge devices are present. Moving ahead to CLI verification, as we can see, show OTV adjacency, that shows you the host name, the destination address, and the status up. The most important one to talk about is the bottom one. Show OTV route. What do you see here? Two lines. I have just highlighted 2 lines over there. It has a MAC address. Talks about the BD engine, BDENG that you can see, and the next hop is there. What does this BD engine mean? That means this MAC address was learned locally. It is a MAC address present in the LAN of this particular site. If we look at the last line, it says that the MAC address, then it says that the AD is over ISIS, and it says write ASR. What does it mean? That this particular MAC address was learned via ISIS from the neighboring site. And the name itself is resolved, as you can see. Not only the IP, it resolves the name too. That is write ASR. Let's talk about the data plane of OTV. What does the encapsulated packet of OTV look like? Once encapsulated, it will add a 42-byte header on top of your IPv4 packet. What it does is takes the classic Ethernet frame, which is coming from the LAN side, scratches off the 802.1q header from it, gets the VLAN ID out of it. Along with the VLAN ID, it pushes the OTV instance that we are running on top of it, the overlay number we are running on top of it, and pushes it as an OTV shim. Via this process, it adds a overhead of near about 42 bytes. We'll check that in the later slide. I have Wireshark captures with OTV that will tell us clearly that it adds a 42-byte header. Now, one important point to note over here is when these encapsulated packets are created, they are created with the DF bit set. What that means is at any network, at any hop, if the MTU is lesser than the size of the packet, it will go ahead and drop that packet. It says that don't fragment it. So we need to consider the jumbo MTU sizing on the network where we are deploying OTV. Okay, till this point, everyone clear? Just some OTV-related basic stuff. Clear, everyone? Yep, please go ahead. You want to enable that? So if I'm getting a question, you want to enable fragmentation? packet will be dropped. Yes, it will be dropped. So because the DF bit is set, so there's a question over here, I just want to repeat it for the whole room, that what happens if somebody tries to fragment that particular packet? It will get dropped because the DF bit is set. To get over it, if I have to add more to your answer if I can, to get over it, there are a few commands. We don't recommend it normally, but there are a few commands that we can use while in the overlay interface itself, we can run that command, and after that, fragmentation will be allowed. Yeah. Clear? Any questions? Am I going too fast, too slow? All good? Speed good, guys? Language, crap? Maybe. Some other part of the world, what is it talking about? Okay. Moving ahead to the role of ASR1000s in OTV deployment. I love this box. I really love this ASR1 case, working on the ASR1 case. Very easy to debug, very easy to troubleshoot on ASR1 case as compared to some of our ISRs. Let's have a look. What are the deployment roles that ASR1K can take in the world of OTV? There are three types of deployments that we can use: brownfield deployment, greenfield deployment, and the third one is the one which is the most important one in this session, OTV with encryption. If we talk about brownfield deployments in detail, the legacy deployments are something like where customer uses your Nexus 7K, the bigger boxes in the data centers, and he has the old 6500s in the other. What we can do is we can pull up, we can provision for a internal interface from these 6500s. It's not feasible all the time to change the Nexus 7Ks. These are bigger boxes, better performance. What we can do is we can put the ASR1K as the edge device, and from the 6500 we can put an internal interface towards the ASR1K. That will work as the L2 interface. All of the traffic would be taken care till the 6500. From there, the L2 frame goes towards the ASR1K. ASR1K acting as the edge device will have OTV towards the Nexus 7K. The interoperability is allowed in OTV between the Nexus and the ASR1K. Going ahead towards the greenfield deployment. Nothing fancy, just the word might seem fancy to you, but nothing fancy at all. If you're coming up with a new data center, depending on the performance, we can choose our ASR1K models. Directly, you can put the ASR1K as the edge device and build OTV on top of it. The performance is what matters. You want to go for a large data center, probably you'll think of Nexus at one point in time, but there are some ASRs, the bigger series of ASRs, which will be able to provide you that amount of throughput, that amount of performance. The third one, OTV with encryption. It's a single box deployment. Why do we call it a single box deployment? If we choose ASR1K to become our edge devices on which we will have OTV services, along with the OTV, it can provide you both the modes of encryption, be it via IPsec, be it via GetVPN, OTV. On top of our overlay, it is supported on ASR1K. That's why we call it a single box deployment mode. Start off with the most important topic, OTV with encryption. What we'll talk about is a bit of benefits. Then we'll have an in-detail look along with some of the packet captures and some of the tools that we have in Cisco, which can tell you about the overhead that is getting added in both the sections. First one we'll talk about is OTV with GetVPN. Second one is OTV with IPsec. At the end of this section, I'll give you an idea about when to use which mode of encryption that I've tested in the lab. I do have the configs still with me. Anyone wants, just ping me on the Spark room. I'll provide you the configs also. I still have that. Okay. Benefits, as we discussed in the previous slide, it's a single box deployment mode. At any point in time, if we choose ASR1K, it can provide you encryption along with the OTV services. It supports ASR1K, as we know. It supports both the modes of transport, both unicast and multicast. Both of them are supported with the encryption modes. OTV with GetVPN. Let's talk about it. Why do we need GetVPN, first of all? As I spoke before in our beginning slides, some of our data protection laws, it says that we need to protect our data. These data might be some of our academic records, some of our medical records. It could be some of the transaction gateways or transaction application financial data that we are accessing from the other data center. We need to protect that. Yes, there are some technologies, other technologies like MPLS VPN, where we can build a secure channel, a private secure channel of ours. But our company compliance requirements sometimes say that whatever traffic leaves my edge device should be encrypted. That's where GetVPN comes into picture. GetVPN, or group encrypted transport VPN, is a technology that will help us to encrypt traffic that is going unsecured, going via the unsecured network. A very important aspect of GetVPN is that whenever it traverses this data, this encrypted data towards the other sites, it doesn't build dynamic tunnels all across towards the other data center. It's not like DMVPN. If we talk about a bit about DMVPN, what does it do? The spoke sites, they join towards the NHRP server. They have permanent dedicated tunnels built towards the hub site. At any point in time, if let's say the spoke A has to talk to spoke B, a device which is in the LAN of spoke B, what does it do? It will have to query the NHRP server. The server will reply with the real IP of spoke B. Once I have the real IP at the spoke A's end, what I'll do is I'll build a dynamic GRE or IPsec tunnel towards it and then push on the data. We want to get away from this via GetVPN. There's no tunnel at all built in GetVPN to traverse the data traffic from site A to site B. One more important point of GetVPN is that it uses the original IP to route the traffic. This we call as IP header preservation mechanism. So when the packet is routed out to all of those hops towards the destination, they just have to have the information in their own routing table to route the traffic. It seems quite similar, right, to the IPsec transport mode, doesn't it? The header preservation mechanism seems quite similar to the IPsec transport mode. But, however, the underlying IPsec mode of operation in GetVPN is the tunnel mode. Now, question arises, why? Why do we have to go for the tunnel mode? It has IPsec, it has the header preservation mechanism. Why not the transport mode? Yes, I agree to a point that IPsec transport mode, it reuses the IP, thereby saving some overhead. But at the same time, it does suffer from some of the fragmentation and reassembly limitations when used with tunnel header preservation, and that shouldn't be used with GetVPN, where we have to fragment the data, fragment the encrypted traffic. We don't have to use that. That's why we chose IPsec tunnel mode in GetVPN. Again, the GetVPN, it leverages the IPsec protocol suite itself to provide you data integrity and confidentiality. One of the most important aspects of GetVPN is that it allows the code to do the replication. It allows the code to do the replication in case of multicast. It is quite familiar, like it is quite similar to what we do with the multicast transport. Those are some of the points why we chose GetVPN, first of all, to encrypt our traffic. Moving ahead to some of the terminologies that we'll use with Get. That's a diagram, that's a picture towards your right-hand side. And you have a key server, you have your group members, and actually a typical GetVPN deployment would consist of these two routers, the KS or the key server and there would be a GM, which we'll call as the group member. The key server, it can be an iOS or an iOS XE device, which will take care of your get VPN control plane. It will have all the policies, all the access lists, all the hashing algorithm that we need to use to encrypt the traffic. It will have everything centrally located in that key server. Once the neighborship is built, once the control plane negotiation has been done between the key server and the group member, it will push all those policies. We'll have a look at that in a good way, in a packet walk in the upcoming slides. The group member. Group member are the devices which are on which actual encryption and decryption of the data is done. They take care of your data plane. By this time, you would have guessed your edge devices, the OTV edge devices, they will be working as your group members, right? And the key server would be a centrally located device to which the edge devices will at all point in time have connectivity. Let's have a look at the packet walk. Okay, again, there's one more point I was about to miss, maybe. The key server, it also has an important job role to generate the keys. There are two types of keys it generates. A KEK, or key encryption key, and again, a traffic encryption key, that is TEK. KEK, or key encryption key, is the key which it will need to talk to its group members, or at any point in time, let's say there are any control plane messages between the group members or our edge devices and the key server, they will use the KEK. At any point in time, if I have to send some traffic towards the other edge devices, the other group members, I don't have to build a tunnel, as I told you. They will use this TEK, which has been shared by the key server. Based on this TEK, the other data centers or other neighbors in the same group would come to know that, okay, this is traffic from my own group, let me decrypt it. So we don't really build any kind of tunnels when we send this data traffic towards the other sites. It's just based on this TEK, which is shared from the key server. Clear till this point, guys? Am I going a bit fast, or is it okay? Let me know. If I go a bit fast, let me know. Yeah, please. Uh-huh. Mm-hmm, mm-hmm. Not exactly. So just to repeat your question, if I can phrase it properly, let me know if I go wrong. So your question is like, Get VPN will again add its own encryption header on top of OTV. So will there be a performance challenge for OTV? That's what your question is? I'm sorry? On the hardware side? Not exactly, because these are two different technologies working in conjunction together to give you encryption. So once to answer your question in a better way, once your OTV header is prepared, your OTV encapsulated traffic is prepared, packet is prepared, that is handed over towards the joint interface. That is where the encryption will be done. And again, an overhead will be added. Yes, it adds up to the overhead. It keeps on adding to the overhead of 42 byte of this, and probably somewhere around 72 to 76 bytes of overhead will be added because of the encryption. You have to consider jumbo MTU sizing, that's what I told. But performance-wise, it won't affect much. ASR1000 is better performance with the ESPs. You take bigger boxes, it has always better performance with these packets. Until and unless the packet is not getting fragmented, you really don't have to worry about it. It keeps on adding overhead because these are two different technologies, as I told you. They just work together to provide you encryption. Clear? Or any questions at this point? Move ahead. Okay. So what I have over here is a packet walk to see what actually happens in the back end when we have get VPN. I have my edge devices on site A and site B, and the key server is somewhere centrally located. Just to let you know that this key server has connectivity towards all of the edge devices at this point in time. They're able to reach each other. That's all is the requirement. So what happens first? Let's see. A GDOI request packet is created on the group members, and that is sent across towards the key server. If we talk about the underlying behavior, underlying what exactly happens, what are these messages that are getting exchanged? So what they do is, based on these message, I just put a high-end overview of this. But if we think of it, what happens exactly in the backend, there will be 6 messages, or 3 set of messages. Those will be exchanged between the group member and the key server. These 6 messages are the same ones that you'll need to build a ISA-KMP tunnel between 2 devices. If you want more information on it, I really encourage you to put that on the Spark. We can talk more about it. I can give you links. I can give you some debug outputs also, which can show you what are these 6 set of messages, or 3 set of messages that pass in between to create an ISA-KMP tunnel. So the underlying technology is something like this. At all points in time, the key server would have a permanent ISA-KMP tunnel built towards the group members. Any kind of control plane traffic that we need to send will be via these ISA-KMP tunnels. What about the data traffic? Does anyone have a question in mind that if data has to pass, it has to pass via key server? Anyone? Please. Actually, there is a consideration. Yes, that's a good question, actually. So the question is something like this. Can we make one of our edge devices as the key server itself? So there is a restriction in GetVPN that we can't do that. Your group member at any point in time can't be the key server. There is a restriction. You can't do that. I'm sorry? Yes, we can have redundancy. I could have put that, but that would deviate us from the topic. Yes, we can have redundancy. Good point again. The key server, we can have 2 key servers at any point in time. I'm sorry? Up to 8 devices, you mean? Okay. Yeah. We can have redundancy, for sure, about the key servers if you're talking. Security guy? I'm not. I'm not actually a security guy. I mean, the points I learned over in this presentation is that I've worked with some of my security folks, security teammates in TAC, and that's what I've learned till date. Any point in time if you have, but don't restrict yourself asking those questions. I'll note that down, or just put that to the Spark room. I'll ask one of my security, I'll work with them and get you an answer. I really apologize, but because of the India and US time zone differences, couldn't find a Spark manager who can answer your queries then and there itself. But be rest assured, go ahead, post it. After our session, we can have a bit of discussion in the Spark room. So, as we were talking about, a permanent ISA-KMP tunnel would be built between the group members and the key server. Once this tunnel is built, what do this reply packet have? Let's have a look. It will have all the centrally located policies that are put onto the key server. All the policies, all the ACLs. What are these ACLs again? That will tell, these are the ACLs which will tell the group members that what traffic to encrypt, what not to encrypt. The interesting traffic, basically. And the 2 important things, the KEK and the TEK. That will be pushed from the key server towards all the group members. The policies, the ACLs, the KEK and TEK, these are the 4 things that will be in the GDOI reply packet, and that is what will be installed on your edge devices. Yes, please. Mm-hmm. It can. I mean, a group member, as I told you, it's an iOS or iOS XE device, end of the day. I mean, the group member, if you're talking about?
The group member, like if you have a mixed environment, you have a 7K doing OTV at one of your sites, in your 7K,
Okay.
be the group member itself.
I don't think there should be. No. I mean, his question is.
Yeah, the gift VPN piece. And you can,
Okay.
if you're doing the encryption on OTV and one of your edge devices.
You have a mix of devices, basically. So the question here is, I'll just repeat that for the room. So the question here is, the edge devices, we have a mix of devices, let's say. We have ASR1000 and we have Nexus 7K at one end. So would this get VPN setup work if we try to put? Shouldn't be a problem. I haven't tested that for sure, but I can answer this question to you after this session. I'll need to dig deeper into it. As I told you, I'm not part of those Nexus 7Ks who I don't handle that, but I'll surely answer this question. I'll keep that in mind. These testings, what I've done, guys, till date, is on ASR1000 HX and 1001 HX, one of the newer platforms in ASR. If you want to know more about these platforms, just out of the topic, I just want to go out of the topic a bit. If you want to know more about these ASR platforms, I do have a session tomorrow. I do have a session tomorrow at 1:30, same time. It's a 1.5-hour session, and we'll be talking mostly on the architecture of those two platforms. And these testings, I concentrated on those devices only. That's why I have put specifically that it's ASR1000 OTV. But I'll surely take this as a question. I'll answer that to you after the session. So now let's see if the get VPN control plane, now that we have built those permanent ISAKMP tunnels, how would it behave in the OTV setup? Let's have a look. At this point in time, I have the same thing, just the OTV tunnel built. The overlay has been built between both the sites, and I have multicast core there. We assume that at this point in time, the key server has built those ISAKMP tunnels and has negotiated those KKs and TEKs towards the group members. Now let's see what exactly happens. What is the order of operation when these L2 frames come in and when they have to send some MAC address related data towards the other data center. Let's have a look. So what happens? First, the MAC table is created in the local site. I learned MAC A, MAC B, and MAC C from 3 of the VLANs. Anyone wants to answer? How did I learn that? Whoever answers, cup of coffee with me. Flooding. So at some point in time, these MAC addresses would have sent some data, and that's how I learned it. Sure thing. We'll have a coffee. Okay, now, what it does after that, OTV crafts an update packet out of it. This update packet is now encapsulated via the overlay interface. And what do we have? The update packet encapsulated, and the header, the topmost header, would have the S,G information. Source as IPA. No, it's really IPA, not Indian Pale Ale, the beer. It's not that. It's IPA towards group G. That is what is populated over there. Once this encapsulated packet is created by the overlay interface, it hands over that packet to the join interface for further encryption. Let's see what the join interface does. It encrypts the packet, puts the TEK, because from the ACLs that we define, we'll have a look in the configuration section, from the ACL, it knows now which traffic I need to encrypt. It knows that this is one of the data traffic. I need to put TEK in place, and then sends it across towards the multicast core. In the core, the packet gets replicated, sent further towards the other neighbors. Now, what happens with the neighbors now? Just a reverse order of operation. First, we had encapsulation done. Then we handed over the packet to the join interface where we had encryption, and then towards the core. The same order of, the reverse order of operation will happen at the neighbor end. It will decrypt the packet based on the TK values. It will match this TK. Yes, please. No, no, no. Those are part of the same group.
Yeah, 3 and 4 aren't. I asked about 2.
I'm sorry?
2 is a different group. 2, GM2 is a different group.
No, no, no. It's in his local site. It is in his local site. It's part of one site itself. Site A has 2 routers, multi-homing, and this particular update packet, anyways, will reach to site 2 also, via the site bridge domain itself. It will. It doesn't have to send that again encrypted towards his own site. It's his own site data. Did I answer your question properly? Was it good? Good? Okay. So what happens here is that first decryption will happen, and this decryption will happen based on the TEK value that we have got from the key server. The key server, when it negotiated on the control plane over those ISA-KMP tunnels, would have shared the TEK and the KEK, and the same TEK and KEK would be used by the group, by the whole group. Based on this TEK, it will just go ahead, decrypt the traffic. Now we have the encapsulated OTV packet ready at the other end to be fed to the MAC table. Once the decryption is done, the packet is handed over towards the overlay. What it does, it decapsulates the packet, gets the proper update packet which we want to feed towards the MAC table, and that's how this update packet goes towards the MAC table. Now, the site B knows that if I have to send some traffic towards MAC A, B, or C, I have to send it to the joint interface of site A, that is IPA. Clear, everyone, with this packet walk? Or any doubts, any questions? Yes, please. It's user-defined. It's user-defined. You can use any of those. Yes, exactly. So the question here is there any specific group of multicast that we'll use if I have multicast core? You can use, it is user-defined. Whatever you specify in the configs, based on that, it will judge, okay, this is my control group traffic, this is my data group traffic. That is in the overlay configs. Just 2 things you have to mention. One is which group, which multicast group your control plane messages will pass. Second one, it will tell you which group my data group is my multicast data group. That will define in the configs. It's user-defined again. Clear? Yes, please.
Is there one recommended over another, multicast versus unicast?
Oh, you mean the, so if I can phrase your question properly, so you mean that where would you go ahead and use unicast and where you do, I mean, which encryption mode for what? Right. Is that the question?
Is always OTV is always multicast?
No, you can use unicast also. You can use unicast also. That's what I told you. Once I go to the next section, I'll clear up this question. So your question basically is, what encryption mode would you go ahead and use? Or is it only specific to the multicast group? No, it's not. You can use unicast core also. Why I put that, I'll answer that question. Why I put this particular slide and get VPN to work with multicast core. I'll tell you what's the logic behind that. Yes, please. Yes, that's the requirement. That's the requirement for the control plane. So the question here is something related to the considerations that we took in the previous slides. That do we require a rendezvous point at any point in time? Yes, we do. The OTV control plane, the requirement, as I said, it will be ASM, that is any source multicast with sparse mode. So we need a rendezvous point. We can have dual rendezvous points also. That will add more complexity, yes. But we can have that, yes. To answer your question, it will have a RP. Somewhere in the multicast core, it will have a RP. And that is the RP with which all these multicast groups join in. That is from where they will get the S,G information populated. Clear? Move ahead, guys? Okay. Let's talk about the most important part again. What is the overhead that is getting added? It's not for free. I mean, there will be some pros and cons to everything, right? We take OTV into picture, it adds a 42-byte of header. That's its con part, I would say. Again, we have encryption on top of that. your MTU, your overhead will increase. So this is the format that your encrypted packet will look like. The payload would be the original OTV packet encapsulated with the 42-byte header added. It copies, as I told you, it has IP header preservation mechanism in GetVPN. So what it does is it copies the outer IP, adds 20 bytes again, and in between that, it has the ESP header added, which is near about 52 to 56 bytes. When I was putting these things onto the slide after testing on my lab, I said, why stop here? Why not give you guys a perfect example or just capture those packets and show you exactly how much overhead will be added? That's what is in the upcoming slides. So I captured a packet, did a very simple test on my setup. Ping. Used a 1,000-byte ping packet without any kind of encryption. Took a snippet out of it, and that's where you can see the total length is 1042. A 42-byte of header is added only with the OTV encapsulation. Now let's put encryption in this lab and see how it behaves. What do we see? Size increased to 1116. So near about 74 bytes of encryption header is added if we use GetVPN. To our OTV packet, to that poor ping packet which I sent with 1,000, now it has become 1116 with OTV encapsulation and added encryption header on top of it. I was more curious to know what are these headers getting added that makes this encryption header as 74 bytes. Anyone in the room has used the IPsec overhead calculator tool of Cisco? Anyone? Can I have hands? Oh, great. Then you know what I'm talking about. So I went to one of the security TAC engineers. I said, dude, this is what I've captured. Is this correct? It says, gives me a solution like this. Use the IPsec overhead calculator tool. You'll come to know if whatever you have captured is correct or not. I'll give you the link in the upcoming slides. So if you look at the IPsec overhead calculator tool, it's a very simple tool. And this is how it looks like. What you have to feed to that tool is the original packet size. It is 1042, we know that. With encapsulation, it is 1042. That you feed it, the IPsec transport settings, that is maybe the versions that you are using, IPv4, the tunnel mode, the mode of encryption that we are using in IPsec, underlying mode, IPsec tunnel mode. Click that, give the ESP encryption that you're using according to the configs. I was using SHA-256 HMAC that time. You hit enter, and this is what it shows you. 1116, exactly the same bytes that I saw in the packet capture. And these are the fields that are getting added when you add that encryption header. Along with the size, it tells you everything about the packet. If you are using encryption in your network, use that tool. You'll come to know what are the headers getting added, what are the fields in that header getting added. Clear till this point, everyone? Any questions? Okay, let's move on. So a bit of configs. Now, what do we have here in the key server? As I told you, key server will be the centrally located device which will have all the policies, all the ACLs, all the hashing algorithms that they need to use, everything defined in the key server. As you can see from the configs here, the crypto ISA-KMP policy, authentication, and crypto ISA-KMP keys. Now, these first three lines are our first set of message that is exchanged to build that ISA-KMP tunnel I told you. 3 sets of messages are exchanged. This is the first set of exchange between the key server and the GMs. They authenticate each other. Apart from that, what do we have? We have the transform set defined, we have the group, the identity number, and along with it, I've just highlighted that part, match address IPv4 GM_ACL. That is the ACL which I have defined in the key server. There's very minimal configs to be put on our edge devices related to crypto. Just to build that control plane negotiation, whatever configs is needed, that is only which we'll have on the group members or the edge devices. We'll have a look at it in the next slide. What do we have in the GMACL? Something to note over here. I have a bunch of deny statements. You see that? And at the end, I'm permitting everything. This ACL will be pushed towards your group members or the edge devices. Based on this, the encryption will happen. Based on this, the group members will come to know what traffic to encrypt and what not to encrypt. There is a consideration again in GetVPN that we do not encrypt the control plane messages, the control plane traffic. That is what you see in the deny statements over there. You don't encrypt any BGP traffic. You don't encrypt any ISAKMP or NTP related traffic. You don't need that, right? Those are control plane messages, won't have any information. Even if somebody looks at it, it will just be those CS6, CS7 traffic, DHCP values. The first line is, one of the important things to note is, I'm denying UDP any to port 848. This 848 is the port number on which the control plane negotiation of GetVPN happens. So if you have some firewalls in between, if you know that there is some firewall in between, allow that port 848. Otherwise, they won't negotiate with that ISAKMP tunnel. There are two more lines highlighted also. Deny IP any 239.2.3.4. Some multicast group, to answer your question, there was a question some time back, that should this be user-defined? Yes, this is the user-defined multicast group I was using for the control plane negotiation over the multicast core. And you have to deny that group. You don't need to encrypt that traffic at all. The other one, it's a deny statement for UDP any port number 8472. Anyone aware of this port number? Come on, guys. I need answers, maybe. Just talk to me. So this 8472 UDP port is the port on which OTV sends his own control plane messages. I'm just giving you an idea about these port numbers because let's say that in your network you have a firewall or some policies that you have to enable such amount or a certain amount of ports. Take care that you should have these ports open for the traffic to flow. 848 for GetVPN, 8472 for OTV. That is the UDP port on which the OTV control plane message passes. And at the end, I had the permit IP any. That'll tell the GMs that any traffic which is in these deny statements, you do not encrypt it. Just send it as a clear text. Whatever it is, send it across. Apart from this, you do encryption on top of that. Put your TEKs, send it across towards the group. All these policies, again, I want to tell you, stress on this point, all these policies, all these ACLs would be in the key server, centrally located. I won't, if I have to, once the negotiation is done, these ACLs will be seen in the group member or on our edge devices. Okay. Moving ahead towards the configurations that we'll have on the group members. Very minimal config related to crypto. Just the ISAKMP keys, the authentication defined over there, and I have the group number and identity. These particular lines of messages, these particular lines of configuration will be required for us to build that ISAKMP tunnel in the first place, to build that control plane negotiation between the key server. So here's where the crypto map is defined. Name of the crypto map. We have come this far. I just want to ask one more question to you guys. Where will I apply this crypto map? Anyone wants to answer? Where will I apply this crypto map on my OTV edge devices? Yes, on the group members, which interface shall I apply it? Join interface. 1, 2, 3, 4 coffees, okay. Okay, join interface. That is where the encryption will be done. The job of the overlay stays the same. It will just encapsulate the packet under which mode of operation, under unicast or multicast. That's all. It'll hand over the packet towards the joint interface. That is where the encryption engine will come into picture. It will add the encryption header, send it further towards the neighbors. That's what I have in the next slide. The joint interface is where I will have the crypto map defined. Please. Yes.
What you just described there was, I'm having to tell a group member about all the other group members. Am I losing scalability there by using multicast? Am I missing something there?
Can you come again, please?
Scale.
The scalability limit?
Right. So you're supposed to scale by not having to tell a group member about all the group. The reason you use multicast, right?
Yes.
So I don't have to tell a group member there's 17 other group members.
You don't have to tell. You don't have to tell that because
Isn't the whole point of doing all this so I don't have to tell a group member that there's 17 other group members out there?
Are you doing that? I mean, so if I understand your question correctly, is that if we keep on adding other group members, how will one certain group member come to know that I have these many group members in place?
That's what I'm saying. If we're doing all this key server stuff, then I don't need to know because
Exactly. That is, everything is taken care by the key server. With this key server in place, it will just check with the group members that what is your group ID, what is your group name. Based on this group ID and group name, it will build the neighborship. At any point in time, you don't need to know that. That's what is different from DMVPN. We spoke about it, right?
Right. So then you go back one slide.
Okay.
Why do I have to tell group member 1 that 2, 3, and 4 exist? That's the problem.
Okay, I mean, I took the slides again, but if you remove that also, won't hamper. At any point in time, it needs to build the ISA-KMP tunnel with the key server itself. That's it. Once the ISA-KMP tunnel is built, your job done with GetVPN. Nothing else do you require over that. I was keeping on testing, so while taking the snippet, maybe these configs are there. Good point. Good, well noted. Answers your question, correct?
Yeah,
okay.
I'm not going to add map statements 2, 3, 4.
You don't need to tell those group members at all. Because, as I told you, the data plane, they don't build any kind of tunnels, any kind of dynamic tunnels. It is all done with that TK value that it gets from the key server. So it doesn't have to really care about how many group members do I have. At any point in time, if it is a data traffic that is matching my access list, I'll encrypt based on the TK, send it further, let the code do the job.
I think it's 2 things, right?
Please, go ahead.
You got the multicast, just for OTV itself, so you wouldn't have to do any additional configuration, but because we're encrypting it, that's where you have to add all those individual tunnels each time.
You mean the tunnels from...
We were just talking about a second ago.
Mm-hmm. Okay.
Right there, we have the crypto ISA-KMP key defined for GM2, GM3, GM4. Is that really correct on the group member? Isn't that more just on the server to where you have to define each?
Yes, this will be defined.
You only need the ISA-KMP key to point to the key server.
Key server to GMs. That's all you need. That's what he noted out. Like, why are these lines in the config? You don't need it really.
Sure, you don't need it.
You don't need those lines really. No, I will remove that. I was taking snippets from my lab devices. Maybe so due to some testing purpose, I would have put it. But for sure, at any point, we will check that in the output section. I have snippets of outputs taken, and it'll clearly tell us that at any point in time, if we check, in this setup itself, if we check the key server, it'll have 4 ISA-KMP tunnels built towards my group members or the edge devices. If I check the same ISA-KMP, the number of ISA-KMP tunnels that I have on the group member, on the edge device, if I check, it'll have only 1, and that too towards the key server. I really apologize, guys. That's up. Good point noted. Okay, some verification related commands that we can use: show crypto GDOI, GDOI ACL, rekey, and some of the verification commands that we can use on the group members is OTV detail, VLAN, ISAKMP SA, that will tell you about the tunnel. Let's have a look quickly, go through the outputs. So group name, get VPN1, this is the group name which it will have on all of the groups. The group type GDOI, group members, the number of group members it has is 4, and the ACL configured. These are the pointers or things to look upon in those outputs when you're trying to troubleshoot or when you're trying to do a health check, basically. Now there's one more point over here. The rekey lifetime you see over there. The group rekey lifetime is 86400. That is near about 24 hours. I have put it to default. So by default in Get VPN, every 24 hours, a new set of TEKs and a new set of KEKs will be generated and pushed towards your group members or the edge devices. You can specify the timer as per your configurations or your topology, but by default, it is 24 hours. Even before the key server, actually, even before these timers expire, the key server will create the KEKs and TEKs and distribute it towards the edge devices. For a pseudo period of time, your group members would be using both the keys, the new and the old ones. And once it expires that 24 hours, once it is 24 hours from the first key generated, it will go ahead and delete those older KEKs and TEKs. So, show crypto ISAKMP SA, as you can see, on the key server, you have only 4 ISAKMP tunnels that are built, and that too towards the joint interface IPs of my edge devices. Just as I'm talking about the key server. The summary output will give you a bit of more detail, something like the group name, the identity, and what is the key server ID again. Let's come towards our edge devices and do a basic health check on that. Show OTV detail, normal command. We'll use AD server, state is up or not, any kind of what is the joint interface, what is the ARP cache timeout, everything will be seen. It's normal OTV commands. I'll give you a link towards my previous session. There I used a lot of health check commands in OTV. You can refer that for any kind of health check you want to do on your OTV setup. I'll give you that at the end of the session. Show OTV VLAN, one of the most important outputs that will tell you what are the VLANs active on my site. The active ones in this scenario, the active one was VLAN 13, and VLAN 20 would have been taken care by the other data center. That there will be active, and 13 will be inactive in a multi-homing setup. Show crypto ISAKMP SA, to answer your question. So, show crypto ISAKMP SA on the left ASR, I mean the edge device. It will tell me that I have only one ISAKMP tunnel built. That configuration probably was confusing. It will have only one ISAKMP tunnel that is towards the key server. That's all. So, show crypto GDOI GM, it shows me the local address and port number. The local address would be my joint interface IP, and the port number, as I told you before, it's 848. That is that is the UDP port number on which the control plane negotiation of get VPN happens. Registration status, we'll see it as registered towards the key server 10.10.10.10. Let's move on to the next topic, OTV with IPsec. Any questions you have till this point? Guys? No? Yes? All good? Okay. Moving ahead with OTV with IPsec. Why do you need the transport mode again? With IPsec, the underlying mode of IPsec operation will be the IPsec transport mode. By this time, you all would have guessed. Save some overhead, right? It doesn't really copies that IP header from the OTV packet, but rather it scratches off the IP header itself, puts it on top of it, saves those 20 bytes of overhead. What does that do? It saves some bandwidth for you without any increase in the CPU load. While I was testing, this is what I was coming to. There was a question, where would you use what kind of encryption? While I was testing these, the best suitable for a multicast, multi-homing setup. Go for Get VPN. That will give you the best results. Easy to manage or maintain. If you're going with lesser number of sites, unicast topology, unicast transport mode in OTV, go for IPsec. Lesser overhead added. Okay, let's have a similar kind of packet walk, what it does. OTV packet, your L2 frame comes in from the layer 2 interfaces. Update packet is crafted out, and out of that, it now knows sending it to the other neighbor, that is IPB. Once we have this encapsulated packet, what next? It will hand it over to the join interface, right? That is where our crypto map would be configured. And once this crypto map, what the router will do is it will check if it is part of my interesting traffic. Do I need to encrypt this traffic or not? How would we do that? Yes, you can use permit IP any in that particular ACL. That would encrypt all the traffic that is passing over that join interface. But if we want to be specific, let's say, that I only want to encrypt the OTV traffic, what do we do now? Any ideas, any clues? Yes, create an ACL, but what would I define in that ACL? How do I catch those OTV packets? The port number, 8472? Yes, that's a way. That's a way. But that port number, again, is a UDP port number, 8472, where your control plane messages will be there. What do we do? What is the encapsulation format of OTV? Excellent point. EO-MPLS GRE. It's Ethernet over MPLS over GRE. If we check that encapsulation header, that is what it will have. If we dig deeper into the packet capture, into the Wireshark capture of a OTV packet, that is what it will have. EO-MPLS GRE. Now we know we have a GRE header in that. So what we define as the interesting packet, interesting traffic for the ACL is, will match the GRE. Whatever GRE traffic passes, you encrypt that. Specific, right? So based on that interesting traffic, I figured out that it is GRE. Let's put that to the ACL. Traffic is encrypted, goes towards the other side. Decryption happens. I get the update packet, and the update again is fed to the MAC table. Just one catch point over here, that what do we want to use in the ACL? You catch hold of the GRE packets. If we don't have any further GRE tunnels in these devices and no further GRE tunnels are passing over that interface, you now know that any OTV packet that is created, it will have the GRE header inside it somewhere. I catch hold of those GRE packets. Permit GRE any from this join interface to the other join interface. I get a specific list of my interesting traffic, the traffic I want to encrypt. Clear? Any questions? Okay. A bit of MTU considerations. This is how the packet would look like if I have to expand it. In the middle, I have the payload, the original OTV packet. The outer IP here, it doesn't copy. Since it is IPsec transport mode that it uses, it will scratch off that IP packet, the outer IP from the OTV encapsulation, put it at the end, and between that, your ESP header and trailer will come into picture. Let's run the same test, the ping test. What's the amount of header that is getting added? Let's see that. Yeah. Without encryption, 1000-byte ping packet, it becomes 1042. Now let's see what happens here with encryption. What do we see? 1080, an encryption header of 58 bytes is added. Now if you look at the slide, you might question me. Your payload was 1042. Now it is 1022. Why do you count it as 1022? Any answers to that? Guys? It doesn't copy, it scratches off. The count of copy is increasing, I guess. Okay, so let's do that. So this is the link I was talking about. Go to cway.cisco.com/tools/IPsec overhead calculator tool. This is free to use. You go to the CCO page, you have this tool. If you're going for encryption, try and use this tool. It will tell you clearly what are the headers that are added into it and how much size at the end of encryption, how much size will it be. I choose 1042 version, mode as transport, the ESP encryption that I need to use, and this is what I get, 1080, the exact same size that I captured on the Wireshark. These are the headers that are getting added. And you can clearly see the original data payload, it is 1022 now. It scratches off the the header itself, the IP header itself, which I had in the encapsulated packet, and puts it on top. Some configurations. Crypto ISAK-MP policy defined, authentication pre-share, the ISAK-MP keys, the transform set is defined over here, and I define the crypto map itself with the ACL as ED2 ACL. It's in the second line, the last but least line, I would say. What do we have in the ACL? As we discussed, we catch hold of those GRE packets. Be specific what to encrypt. That is what I'll define over there. Permit GRE host from one joint interface to the other. And I'll apply that again to the physical joint interface. The overlay interface, I just want to put this slide just to give you information about how do you go for the unicast adjacency, just 2 commands. The OTV joint interface I have to define and use adjacency server, the adjacency server IP, the phone book, which we are talking about in the start. I'll have to put the adjacency server over there and unicast only, that's all. Some health check related to this. Show OTV detail, same outputs. The show OTV detail would tell you the joint interface, the IP address you're using, the mode of transport you're using. And again, show OTV route will have the BD and ISIS. When you check this command, if you see a BD, it's your own local site MAC address. When you have ISIS, it's from the different site, from the neighboring site. Show a crypto ISAK-MP SA detail, that is showing you in detail that I have, with the topology I had, only one ISAK-MP tunnel towards, one tunnel towards the destination. Any questions, guys, till this point? So while I was testing this, I figured out that whenever you have lesser number of sites, unicast topology being implemented, unicast mode of transport in OTV, go for IPsec. If you have multicast, the core is multicast, going for a multi-homing setup, larger number of sites, larger number of edge devices, go for get VPN. Cool, we'll go ahead to the next section, last one. Okay, what do we have here? OTV with redundancy. So, what is this elephant in the room? OTV and redundancy? So I was just talking to my friend over here before we started our session. I had a customer coming in just 4 to 5 months back. What I said is, he had some issues with, he had 3 sites actually, and all of them had unicast transport. That's what he wanted to configure, OTV unicast mode. Had a few glitches in the config. I corrected them over call. I was just discussing about some of the health check commands. Then he comes up with this idea, tells me, okay, look, Uma, I have a DMZ cloud in my LAN, my private DMZ cloud, and all these data center have link towards those DMZ clouds. Can you tell me a way how I can go ahead and configure redundancy in this setup? I was puzzled. I have really never seen till date any of the customers going with OTV and redundancy at the same time for the OTV traffic. That's the biggest elephant in my room at that point in time. The first thing I thought is, do I have to put again a new overlay for this redundancy? What do I do here? I gave him a solution at the end of the day, till date, working as a charm. No issues seen till date. We'll see what restrictions are there and what did we do to resolve this problem. How did we put it as a redundancy setup? What we have in this section is some of the benefits that we achieved out of that setup. The topology design, of course, the configurations that we are using, and a test case with a packet walk we'll see how exactly the packet traverses towards those LAN links which he had towards the DMZ cloud. Let's start with the benefits. This was his statement actually. I love redundancy and I had to adopt it from there. Who doesn't love redundancy, right? We always want to minimize our downtime. He had one link in the backend, one link towards those DMZ cloud. We suggested him, why go with one link? Put it as a port channel. Bigger bandwidth you'll get, better bandwidth you'll get. Increase the bandwidth of the link. And the end of it, automatic switchover. We don't need any kind of manual intervention or any other feature, I would say, to switch over the traffic when the underlying transport goes down. Let's have a look at the topology. I'll tell you a restriction over here. So this was his basic topology that he had. He had 3 sites, unicast deployment, and each had one link towards those DMZ cloud, his private DMZ cloud somewhere. I said, okay, if we're going with this, let's start with the basic. Put 2 links, put it as a port channel. Let's see if it supports. We put that to port channel. That is one restriction that we need to keep in mind. I did tell him on call. I told him, at any point in time, let's say your join interface goes down, what will happen? Your physical join interface goes down, that will take your overlay down. You won't have redundancy in that matter. He said, I know this. You don't have to tell me. Because it's obvious that the physical interface, join interface goes down, we won't have. What I'm worried about is, I'm having BGP neighborship with that internet cloud. At some point in time, let's say if the BGP goes down, what do I do then? My join interface is up, my BGP has gone down, the underlying transport has gone down. Give me a solution which will fit this. That made my life easier after that. I took 2 days just to set it up in the lab, to test, to get that confidence that yes, this can work. What we did is, this was his actual setup. He had 2 overlays on each of the devices. 2 overlays on each of the devices. We configured a port channel towards the DMZ cloud, and this is what he had. He had BGP running with the internet cloud, with the Ps. What we suggested is, in the LAN, these port channels would be plain L3 interfaces, no OTV configurations on them. What you do is, put these port channels as L3 interfaces, run OSPF on top of it. Let's have a look at the configurations, why we went for OSPF. So this was his overlay configs. I just took it from one site. There are 2 overlays, one going towards site C, one towards site B. Plain, simple, normal, nothing fancy about it. On the same join interface, I have 2 overlays configured. That's all. This is where the change in configuration comes. What we did is, the port channel, which I defined over here, this is the port channel configs I have in the bottom, plain L3 interface. What we did is, run OSPF, advertise those port channels in it, advertise even the join interface IP, make it as a passive. Why passive now? I don't want to send those OSPF hellos and updates and everything onto that particular join interface. It's running BGP, why bother it? I just want to advertise that join interface so that everyone in the site can have reachability over the LAN also. That's the whole change that I did in his network. This is just the chunk of config. I wanted to see if it works or not, and didn't think at that point in time it was so simple. So let's have a packet walk. Update comes to site A. It recognizes this for site C traffic, sends it to site C. Let's say one more MAC address wants to talk to site C again, and at this point in time the BGP goes down. What will it do to the routing table? Overlay interface encapsulated the packet, handed it over to the join interface. How does the join interface send the traffic to the other join interface? Routing, plain, right? I should have a route in the routing table for that particular IP address in the destination. BGP went down. It took those BGP routes I had from the routing table And what will it install now? The OSPF. The OSPF. Simple routing. I don't have to do anything at all. Automatic switch over. Yes, please. No, it can't. It is not supported. We have, actually to answer your question, we have put an enhancement towards the OTV team, but what they figured out is if we put that as a loopback, it will break some of the additional functionalities, some of the current functionalities it will break. That's why they are not going for it, but the enhancement is still active. We will figure out, maybe in the upcoming days, we'll figure out a way. So now what happens? It has the route installed, goes via the OSPF, goes via the DMZ cloud itself, the OSPF route. Let's have a look at the outputs. Ping test with 100 packets goes fine. Knowingly, I go ahead in my lab device, shut down the BGP neighbor. I didn't shut down the joint interface. I shut down the BGP neighbor. What it does, when I try to ping, just one single packet, it drops. Just one single packet while it automatically switches over to the OSPF or installs the OSPF route. Let's have a look how it affects the routing table. Earlier, when everything was up, idle scenario, going via internet, if I look at the routing table, the routes for those joint interfaces of other sites, they were learned via BGP. When I took it down, what it does, removes that route, puts the OSPF route into it. 80 for BGP, 20 for this, 110. It stays in the backup, not in the routing table. Until and unless there is a BGP route, it is not getting installed anywhere. There's one more point also I added to him. Okay. The BGP goes down, the OSPF route is installed. What if I have a flapping link? What do we do for him? Anyone? Help me with dampening. I suggest him go for some dampening solutions. That it flaps for like 10 minutes, 15 minutes, whatever time. You don't install that BGP route. Let it take the DMZ path. We have better bandwidth on it. Dampening is a very easy solution to this problem. We could have gone for some IPSLA, some EM probably, or something like that. But again, why do we involve additional features onto it when we have such kind of features in BGP? Yes, please. Could have done that. Could have done that. I just wanted to play around with the protocols. Until and unless, so the gist out of this exercise, this particular setup, what I got is, until and unless you have a route to reach that joint interface, there'll be no issues with the OTV traffic. Just keep in mind that your joint interface doesn't go down at any point in time. You have a route towards the joint interface, you're all good, you're all set. Let the primary go down, no issues. If you have a backup path via which you're able to reach that joint interface, OTV will still be able to provide you services. No issues with that. It's just because of the segregation. Segregation as in, the overlay interface has its own job role. Encapsulation, that's his all. Hands it over to the joint interface for further routing. Clear till this point, everyone? Okay. Come on, flip the slides. I didn't stop there. It was going on back of my head that, okay, I gave him a solution, but there are chances that this interface, this joint interface might go down because it's not in my control, it's going towards the ISP. Something happens at the ISP end, the interface goes down. What next? The best suit for these kind of redundancy deployments, I would say, would be OTV on a stick. Anyone aware of OTV on a stick? You attended my session? Okay. I did deliver the session previous year here itself in Vegas. I delivered that session, OTV on a stick, a 90-minute session. That's the link to it, PRKDC and 2100. Take a note of it. It has all the OTV health check related commands, and it'll give you a brief about how OTV on stick is. It's a plain simple design. Just one question you have to ask yourself, where exactly is my join interface? In OTV on stick, what we do is, just have a look at the diagram there on your right-hand side. The edge devices would have only those internet links. Your OTV services would be provided by the ASR1000 sitting in the back end of these edge devices. I'll have one single interface probably connected towards these edge devices. Could be some 6500s, could be any router in that matter. So your joint interface now for your OTV services is in the back end of the edge devices rather than being on the edge device. That is what a OTV on stick deployment is. So now that interface which is coming from the edge device towards the ASR1000, I figured out, just a color combination, I've used L2 and L3 that can be on a single interface itself. In OTV on stick, we have the provision. We can put it on a single interface. So now that link is in my control. It's in my LAN. I have control over it. And I know that it might not go down that frequently as it were with the ISP. This particular solution, this particular redundancy deployments best suit our OTV on a stick, because my joint interface won't be affected even if there is a problem with the primary ISP. Let's say I have two ISPs. I have two ISPs and I have two different connections towards the internet cloud. Primary link goes down. Still, your joint interface in the back end will be up. Your OTV is up. When the traffic is routed towards the edge device figures out, okay, my primary link has got down, but I still have a route towards the other site. I'll route the packet to it. Clear, everyone? Okay. That brings us quite towards the end. Some of the key takeaways from this session. OTV, it changes the game. How does it do that? Two features it implements. One is dynamic encapsulation and protocol learning. We had a look at the key roles of ASR, the brownfield deployment, greenfield deployment, and OTV on encryption in detail. Again, in OTV with encryption, we had a look about both the modes of operation. OTV with GetVPN, with IPsec. GetVPN adds 74 bytes of header, encryption header. IPsec, 58 bytes. Touched upon a bit on the OTV with redundancy deployment. Hassle-free implementation and easy to use, automatic switchover, no manual efforts required on that. And the best suit for these kind of OTV on redundancy setup is OTV on a stick, because your joint interfaces are protected. It's in your own control all the time. As I told you in the first slide itself, do use the Spark room. If you have any questions, we can have more and more discussion on top of it. You want any links, you want any documents to prove that, you want any health check commands, I can answer on top of that. It's available till July 3rd. You can use that. Any questions, guys, at this point? Yes, please.
What if you want to have two ASRs? So you have, for a lot of our customers, they get nervous about having just one device on each side. So two ASR deployments. If you want to have two routers, what other, is that recommended? How does that work? How do you?
Isn't that, okay, so your question is, can I have two ASR in a single site? Right. That's what we do with the multi-homing, right? We have two ASRs in a multi-homing setup. What do we have? We have two ASRs on site A, we have two ASRs on site B. At any point in time, anything happens to the ASR A, it goes down, let's say it crashes. Vulnerable to crashes, Cisco devices. Okay, it crashes. The traffic is taken care by the second ASR itself. You don't have to worry about it. In a multi-homing setup, you already have two ASRs taken care.
You have two overlays, correct?
No, why would you have two overlays? It's only one single overlay. At any point, so it's a feature, it's an inbuilt feature, multi-homing, as I told you, right? It detects that who is his own site router via the site bridge domain that we define. It detects whoever is the other site device via, again, if it is coming from a different site bridge domain, the ISIS net IDs which are configured, you don't need to configure it basically, it will be inbuilt. It will come to know that these are my neighboring devices. How does it load balance the traffic? What does it do? I told you, the show OTV route command. You saw there, one VLAN, two VLANs I had. One was VLAN 13, which was active. The other one VLAN was inactive, right? So at any point in time, this 20, this VLAN 20, which was inactive, would be in this router. Just consider it like two sites, two devices. VLAN 20 active on this one, VLAN 13 active on this one. I still have one more device over here. This goes down. The VLANs which he was carrying, now he will be able to carry that VLAN. That is an inbuilt feature. Multi-homing is an inbuilt feature in OTV. Yes, it's even odd. Of course, you can't change that. If you have all even VLANs, of course, one of the device will be taking care of it. It does the load balancing, as correctly said, that it is done in an even odd manner. You have even VLANs, you have odd VLANs. Based on that, it will segregate the traffic. Odd VLANs taken care by one, even VLANs taken care by one. But what if we have all evens? Can't do that. It will be taken care by one of the devices which is chosen. Okay, guys, fill in your surveys, get a chance to win $750. Do fill in your surveys, give me suggestions, what I can improve on. Probably I went through very fast. I still have 18 minutes, I can see on my clock. Okay, and keep continuing your education. Go to the WISP lab, visit the WISP labs. We have those technical solution booths just right across the WISP labs. Go there. If you want to talk more about it, there are dedicated, I would say, how would I say, dedicated DSCs over there who talk about all the routing solutions, all the switching solutions. Good bunch of folks over there. Very senior in Cisco, I would say. I met them. I met few of them while I was discussing this particular presentation. Met few of them. Go there, meet them. Whatever you have, discuss with them. Routing technologies, switching, overlays, how do I say, VXLANs, any kind of solution, they have a booth for that. Just visit that booth. All good folks, you can talk to them about your issues. They'll surely help you out with that. Keep continuing your education, guys. Thank you. With this, I really thank you for bearing with me for this more than 1.5 hours. Thank you.